So if mu not equal to md not equal to ms, then this means that u3 is broken into u1 3 times to the power of 3, or rather u1 cross u1 cross u1. So this mesh, later we will see in the CKM matrix that the requirement you see this mesh matrix M, which can be written in terms of unitary matrix, say mu 0 0 0 md 0 0 0 ms. If they are all distinct, if they are all not equal, you transpose. So this assume that mu less than or equal to md less than or equal to ms for some u, the unitary group member of the symmetry group. I mean, special unity group 3. And this metric M must be a Hermitian for the strong interaction Lagrangian to be real. For the strong interaction Lagrangian to be real. Later we will talk about symmetry breaking, where this is not followed and you start to have a non-zero off-diagonal matrix. And then you start to have mixing. Quark mixing, or what you call the CKM matrix. Okay? The role of strong interaction in the early universe. That is the. I will put that later. Okay? When we discuss about possibility of the quark-gluon soup during the Big Bang. Okay, so for strong interaction, I think we shouldn't go in very detail. We just finish at that. What is important in the exam actually is for you to draw this octet non-net apa semua ni. That one every year come out. This question every year. Okay, so last time when I I go now say to you about the K long and the K short. Remember one month ago or more about the K on system where you have the K long, K short. And that time we believe that K long and K short are truly CP states, in the sense that they follow CP symmetry. But I think not far after that proposal by, no, I can't remember the Italian name, who proposed this CP states. Later, experiment by Christensen, 1964 maybe, if I'm not mistaken. Proved that the KL and KS CP states are violated, meaning they are sometimes violated by 1 in 1,000 roughly. If I'm not mistaken, to be correct, it is by about 0.003, meaning 1 in 1,000 or 3 in 1,000 CP states. There are one that does not follow. Actually, not correct. Not Christensen. Cronin and Fitch. In fact, Cronin and Fitch get the Nobel Prize in 1980. For this discovery. So it took them 16 years to get the Nobel Prize. For that time, they don't understand that CP is important. Now, the strong and electromagnetic interaction are not affected by CP symmetry. I would say they are invariant, to be very accurate. And the CP operation. Actually, until now, nobody knows why. And CP violation, but violated in weak interaction. So weak interaction, something about this weak interaction. Again, the mechanism of CP violation nobody knows yet. Let me describe in brief CP violation in the standard model. Meaning what? Strong EM and weak together. point number 1, so-called direct CP violation. Direct CP violation is allowed, because there is an indirect one, is allowed in standard model if a complex phase appear in CKM matrix. This one I have not described to you, but you cannot run away. Describing quark mixing. Or P, M, N, S matrix describing lepton, or rather neutrino mixing. Now CKM, Kabibo Kobayashi Maskawa. I think I always get wrong. P, M, and S also, I get worse. I only know Ponticorvo, and then I don't know what is the rest. Something. We will know that later. So already I told you about quark mixing and also neutrino mixing. Later also there will be neutrino oscillation. So it's just mixing. The neutrino oscillation are just neutrino mixing, but change with time. That's why it's called oscillation. Remember, the leptoquark family is, three leptoquark family. The electron with the electron neutrino, up down, and then muon neutrino. You have strange and charm, top bottom, and tau. So these are the leptoquark family, three leptoquark family, and they are the fundamental particle that form everything that is in this universe. Kalau dalam bahasa orang ahli kalam, this is called atom. Orang ahli kalam always talk about atom. What makes this universe? So the high energy physicists found that the universe consists of these three leptoquark family. But according to the string theory, all these particles are string, superstring. Okay. Later, if we have time, we will go into that. Now, consider a set of particle and a set of particle A, B, and their antiparticle. Say A bar, like this. And then consider a process. We have seen this in the case of Keang. Yeah. where this particle A start to change into a particle B over time. Similarly, A bar also evolve to become B bar over time. With amplitudes, amplitude means probability. If you square this amplitude, it becomes a probability, m bar respectively. Okay. Before, and if there is no CP violation, this m and m bar must be the same complex number. If no CP violation, m must be to m bar, no CP violation. But now you know that CP violation occur. So let m equal to some m p I theta amplitude. And so this doesn't change, but then introduce another phase term, say EI pi. Why is that two angle? Because one is just quantum mechanical. Okay? Any m can be written in terms of this, okay, without changing anything. Quantum mechanics does not change, because when you square that, everything disappears. But this one here is telling you something that this pi not is something that something else, not from phase consideration. So similarly, you have m bar equal to some m ei pi, ei theta, e minus I pi. Okay. Because we said that m and m bar should be the same, but now because there is a possibility of CP violation, we add these two, and they are different. One is minus, one is plus. Now, if you square this thing, the m and m bar, you will see that they are nothing changed. Suppose, if there are two different roots, for A to become B, or A bar to become B bar, then M can be a mixture of M1, EI theta 1, EI phi 1 plus M2, EI theta 2, EI phi 2. And similarly, I mean, it is not direct, no direct route, but there might be intermediate. So that's why split into two terms. There are two terms here. We will see that there is a difference between M1 and M and M bar. So we will see that the M square minus M bar square is not zero. If there is no violation, it should be zero. Whether it is the particle or antiparticle that is so CP basically differentiate what is happening between the particle and the antiparticle. And CP violation merely means that particle and antiparticle behave differently. In theory, if there is no CP violation, they should be equal. Yeah? Apa bezanya antiparticle dengan particle? It's just the charge that is different, but anything else should be the same. But because of CP violation, this thing become non-zero. Is kalau kita do the calculation, you squarekan ni and you squarekan yang ini, yang dua ni, M bar, you'll get 4 M1 M2 sine theta 1 minus theta 2 sine phi 1 minus phi 2. So the complex phase, what is the complex phase? The pi phase. Yeah? Give rise to processes that proceed at different rate for particle and antiparticle. Different rate for particle and antiparticle. Therefore CP is violated. So this is what you call, if you consider direct CP violation. There's another one called the indirect. So this is the part number 2. Indirect CP violation. And this was the one that was discovered by by this Crodin and Fitch in 1964. What happened was if you remember, a neutral kaon can transform into their antiparticle. So this means the quark is being replaced with an antiquark and the other way around. So and this, if you remember, it was this can be described by a kaon oscillation box diagram. What does this kaon oscillation box diagram?